So good morning to all. This is Anvesh, and now today I'm explaining a topic about the power semiconductor devices and the components of new power converter developments. So, in the world with the increased penetration of wide band gap semiconductor technologies, the FE FEPCON 2015 session on new power devices and high temperature focused on power semiconductors, device and passive components, magnetic and dielectric materials up through integration for the purpose of refining and appropriate power electronic converters by 2025. An important goal was to identify those markets and application where silicon technologies will be remain the preferred choice. The semiconductors are rarely the predominant failure mechanism even in silicon modules. The failure mechanism are usually either the passive components of or the packing. Thus, higher power densities afforded by using WBG semiconductors require those passive capable of operating at high temperatures and having high reliabilities. Presents addresses the state of art and future directions of for the magnetic cores, dielectric materials, and electronic packings integration. Finally, the potential addition fortunes the merits research in a WBG world, such as a new markets capabilities, circuits, architectures, and applications were evaluated. The session was divided into a four main groups: WBG's technologies, silicon technology, passive technology, and power electronic technology. So now the trending in the power electronic converters, first starting with the WBG technologies. Silicon carbide SiC and gallium nitride GaN devices are reaching different levels of maturity, with the several manufacturers already offering devices in different packages. Example: CREE, EPC, and GaN system, GeneSiC and Infineon on semiconductors, Roham, United Silicon Carbide, and Transform. The graphs illustrating output power versus switching frequency and particular areas where specific devices are more stable than others are available from different frequencies of particular areas which specific devices are more stable than other are available from different sources as shown in the figure. So T. Paul Cho from Rensselaer's Polytechnic Institute provided a general overview of state-of-the-art semiconductor device from various application stages of the art SiC devices and major breakthroughs needed for the greater penetrations in a power electronic system. SiC Schottky barriers diodes are became the device of choices for the system between 300 and 1200 volts, which requires an anti-parallel diodes, SiC diffusions, U-shape, and metal oxide semiconductors, field effect transistors, MOSFETs, and have already reached the market either in discrete or module packages. They are used in commercial products like solar and mobility transistor GaN devices from power electronic system under 650 volts has been reached. Finding commercial applications in efficiency and fast switching are design requirements. Developing several GaN power integrated circuits have 6 and 9 devices respectively in the research. So the effect should be produce development relatability to the bidirectional 600 VGAN MOSFETs, 10 kV SiC, bidirectional insulated gate bipolar transistors, IGBTs, SiC MOSFETs, and IGBTs rated above 10 kV and more. GaN based power applications based specific integrated circuits in operation incorporation optoelectronics. This the main issue that should be addressed, the reliability concern, the hinder greater absorption of SiCs and GaN devices, the material quality for moving a large wafers, which should bring needed cost reductions in additional to potential cost saving at the system level. Power packages capable of removing large heat fluxes from these small area devices is based on gallium arsenic and GaN on native substrates do not seem to be viable at the present time, and they require more basic research. And silicon technology, silicon devices continues to be devices of choice for those applications in which high switching frequencies, high temperature operations, and very high efficiencies do not override design requirements, but cost is of utmost importance. uh, Nethermost did it from Infineon delivered a presentation regarding future silicon devices up to year 2025 and indicated that future optimization of a device's cells should improve performance. Silicon superjunction MOSFET continues to improve. For example, the specifications on resistance is currently at 1 ohm to 1 ohm to 2 ohm, but still far from the limit of 0.1 ohm millimeter to from for 600 to 650 volt devices. These devices may be more expensive for voltages above 900 volt silicon IGBTs, and are also improving in performances by working on the plasma profile, particularly near the meters. And new developments on trends based IGBTs continues to extend the silicon limits while providing cost efficiency. High current applications, reverse conducting IGBTs, interacting into the IGBT chips and using dynamic gauge controls to reduce reverse recovery. Other examples of necessity of size and thermal impedances reductions. So inductance allowing the freewheeling of diode with large scale currents. These modules should experience minimal oscillations while when switching the IGBTs. Another research focus is higher operating junctional temperatures for IGBTs currently at 175 degrees Celsius, which is enabled by the copper bonding and diffuse assembly of chips with a target temperature of operation at 200 degrees Celsius. Finally, Shen from the Illusions Institute of Technologies indicated that reducing their on-state resistance as examples of nano IGBT could increase its current capability by a factor of 3. Uh, oh shit, sorry. Chen from the Elysian Institute of Technologies indicated that nanotechnology will be enable in increase of operating voltages of silicon SiC and GaN devices by the reducing their worn states resistance. As example, nano IGBT could increase its current capable by a factor of 3, and nano cool IMOS could have a reduction of 5 in its on state resistance devices, maybe to reductions in size of the needed capacitors.